Hey everyone, we are Subsonic LLC. We're here to talk about our experience making a WebGL game called SONAR. We're coming from kind of a native development side, so just keep that in mind. We're going to talk about many of the techniques we used in terms of engine design and such in order to keep our iteration speed as fast as possible, as well as many of the problems we ran into and the solutions to those problems as well. So I'm Jason Meisel. I am one of the owners of Subsonic LLC. I'm also the graphics and physics dev on SONAR. And I'm currently a student at DigiPenn Institute of Technology, which is a game programming school up in Seattle, where we primarily do C++ development. So once again, that's where we're coming from.
I'm Sean Middleditch. I was the tech director and producer for SONAR. I am also one of the owners of the Subsonic LLC and a student at DigiPenn. And I also worked on the game that led to the inspiration for SONAR a couple years ago.
So Subsonic was formed in about May 2011 by 4 DigiPenn students, the 2 of us, as well as 2 others. And it was basically just to make SONAR. We really wanted to see what WebGL was capable of and what we could do with it.
All right, so these slides will be available online, or they actually are available at this URL or at sonargame.com. There's a link on there right now. And if you have any other questions, you want to get a hold of us, ask anything, shoot us an email at these email addresses, and we'll help you out best we can.
So let's talk about SONAR. It's kind of a puzzle action game with visual sound waves. So essentially you have a gun that you can use to distract enemies and such. It is full 3D using WebGL, and it's got kind of a silly humor to it. It's just a really overall kind of casual, fun game. And so it was made in about 3 months. Go to the next slide. Made about 3 months, so very condensed time schedule. And we only had 3 programmers, a designer, and 2 part-time artists. So extremely condensed time and extremely small team. We then used the Chrome Web Store for distribution, and that's about it. So just to get a bit of context for what we're going to be talking about later in the presentation, here's a video just kind of showing off the different things that we did in SONAR.
Come on. Uh-oh. That's as loud as it gets. All right, so Subsonic was a student game we made about 2 years ago at DigiPenn. 3 other team members that went on to make SONAR. And it was a very similar game. The gameplay was pretty much the same thing with the same kind of humor. But we had this very abstract art look to it because we had 3 programmers, we had no artists, and this is about the best we could manage. We kind of went with this geometry wars kind of thing. Programmer art, essentially, as we like to call it. So this game saw some success. It was a Independent Games Challenge 2000 level finalist, which gave us kind of the opportunity and the drive to go ahead and try to make SONAR in the WebGL context. So if you guys want to check that out, the URL is there. But otherwise, we took this, made a nice 3D version that we think looks quite a bit better. It was a lot more relatable, a lot more interesting. And, so I'm going to talk a little bit about the engine that we made for SONAR. So some of these techniques are actually applicable to games on any platform, not just the web, but we feel that some of these techniques were really helpful in making sure that we could get the project done in the 3-month time frame that we had. All right, so we made our own engine from scratch, and usually this isn't something that's that great of an idea in terms of tight time schedules. You want to take pre-existing components, but we felt that we really kind of had to. When we started the project, there weren't any other JavaScript game engines that we could find that supported WebGL. There were some fantastic Canvas 2D-based engines, but that really wasn't going to work for the look we were going for. We also wanted to make sure we had a completely data-driven game engine and a content pipeline to make sure our iteration time was really super fast. And then we also had those sound wave mechanics for our main gameplay feature that no off-the-shelf physics engine would be capable of handling. So we had to write that from scratch anyway. So there's a few things that we had made up in our mind that we wanted to get up and running as quickly as possible in order to prove the platform, to make sure that actually going forward with WebGL on the web was actually going to work out and not just be a complete and utter failure. So one of the things that we did to make sure we got up and running quickly was we got animated character meshes loading, animating, moving around, really just showing that the 3D pipeline worked properly. We made sure our online integration was working at a basic level to get our accounts synchronizing online, get game data synchronizing, things like that. And of course, we got our physics up and running as soon as possible. Then we also had the core data-driven components as well as achievements, sound, things like that, working at a basic level. So we went with an object-oriented design. Part of this, I feel, is because we have a native C++ background, but it also seemed to really kind of help organize some of the components of the engine really well. So we originally used the Juice library, which is this really nice object-oriented abstraction library available for free online. But there were some performance issues we ran into, some debugging issues that are kind of specific to our needs. So we ended up rewriting that from scratch, but very, very similar API. We also reused a couple other libraries, including GL Matrix, Require.js. We were using Sound Manager 2 up until the release of Web Audio on Chrome 14. Then we were using JSON for data files and an event-driven framework, again, going for the data-driven approach. Just get an idea of what our object-oriented system looked like. This is very similar to Juice if you have seen that at all. So you can define a class, you can define the inheritance. So the has part describes the properties on there as well as what parameters you can pass to constructors, some other basic requirements, and then a list of methods on the object. Fairly self-explanatory, but it really helped us quite a bit. So now I'm going to talk a little bit about component-based design, which is another general technique, but it's something that was absolutely essential to getting things done in the time frame that we went with. So components, it's also kind of called aggregation in some other contexts. But the idea is that instead of having this deep hierarchy of game objects, like you had a base game object, then an enemy class that derives from that, and then a guard that derives from that, and all these kind of things, the idea here is that you have these individual objects that represent small self-contained bits of behavior. You can then mix and match these objects inside of a larger game object to allow a designer to kind of just move components around without having to get a programmer involved and redesign the way a lot of your architecture works. So if you see here this little bit of code, this is actually a JSON file that describes what I call blueprints, some other people call archetypes, prototypes. But the idea here is that for our player type, we can define which components exist on player. So for example, the transform component will describe things, the 3D object properties, like where it is in space, what its rotation is, scale, things like that. And then we also have the player component, which is the object that is based on how to control the player, how to take mouse input, keyboard input, and move the guy around in the world. An animation 3D component, for example, would be the one that actually knows how to draw the animated character mesh on the screen. And then for the components, we can also specify data members that you use to customize this. So the player animation 3D obviously has a very different mesh than the guards would, for example. And there's various other components that we can put together and describes the entire way a player works. There are two other articles online here. The first is Evolve Your Hierarchy by Mick West. This is one of the few articles I've ever found that describes component-driven nature, component-driven design for games. I highly recommend you check that out. And then the second article here is one that I put together on how to build something like this in JavaScript. So you might find that useful as well. So this is just an example of the classical inheritance hierarchy you'd see in a game. Absolutely, or the vast majority of game engines are written like this. And you start running into problems with a hierarchy like this. So a simple example is, let's say we've got this item class that derives from game object. An item has all the logic for how, if the player runs into it, it gets picked up and put in the player's inventory. But let's say we've got this camera object under enemy, and we wanted to add a feature where the player can knock out a camera and then pick up the camera, move it around, and use it against the enemies. Well, now all this logic either has to be cut and pasted between these two classes, or it all kind of moves up the hierarchy and ends up in game object. And you see this in a lot in even some of the AAA engines where you've got these really heavy game object-based classes that have all this kind of functionality that only one or two actual objects would ever need. This is kind of a real problem. So moving on, looking at how a component architecture works, is we've got these individual game objects, and then we load the blueprint, for example, the player object, and this loads these other objects, these components. So what we can do now is, let's say we wanted to change the way guard works. So we got this guard guy in the middle here, and he's got the ears component, which is the part that's responsible for listening to sound, and then responding to sound waves and sending the signals off to the AI. If we wanted to make a version of guard that didn't actually hear sound, then we can just remove that component. There's absolutely no recoding necessary. That's a simple edit in one JSON file, and you're done, and everything just moves on. And that's actually how we got cameras working. There was actually no special case code in the game object system for cameras, despite them being a completely different type of enemy than the regular guards.
So another pattern we used in terms of our engine is called spaces. It is a very simple idea. You simply abstract your game objects out of the engine. Most game engines just put all of the objects directly in the engine, and this is very troublesome in terms of level loading, or if you want to use your engine to run your menu. And so what this will let you do is it means that you can load level 2 into its own space while level 1 is running, and then if you want to switch, you simply destroy level 1 and create level 2. Going along with that, we also have what we call subspaces, which are essentially components for the spaces that allow you to store the game object components within it, however, and organized however that system would want it. So for example, you'd have a graphics subspace, if you go on the next slide. If you were doing a 2D game, you would want to sort them from back to front. If you're doing physics, you would definitely want to do some sort of spatial partitioning. And this allows you to organize your components however necessary while still fitting the space paradigm.
All right, moving over a little bit on the artificial intelligence, which is really kind of a key component of SONAR, it being an AI puzzler of sorts. So the basic tech we used were action lists, which I'm going to go into in a bit more detail here, A star, and then the event-driven nature. So when we started designing the AI, we had to figure out which behaviors we wanted the guards to have. So we got a kind of trimmed down list here. So things like guard location is when the guard stands in a single location, waits for something to happen. Patrols, when they're moving around the map looking for the player. Chase is they've seen the player running after them. The rest of these are, I think, fairly self-explanatory here. But the action lists were kind of the really key part of how we put the AI together. And again, it helped a lot with our iteration time. So the idea of an action list is that it's an alternative to a finite state machine, which is kind of the thing you usually see used in games. But the finite state machines are really inflexible. If you've ever used one, you know that in order to customize it, you're going to have to go ahead and basically make a whole new version of the state machine. You figure out all the different possible transitions. It's a lot of work, and customizing it's really difficult. The action list is a lot more flexible. The way an action list works is you've essentially got this stack of action objects, where an action object is, at its most basic level, just a function that you can call over and over again. So each enemy would have one of these action lists. And then in the action list is this series of action objects. It describes what the enemy is supposed to be doing right now. The actions have a couple other properties that really come into play to customize the way that our behaviors worked. One thing is that an action can be blocking or non-blocking. So a blocking action is one that says that I'm going to keep running every frame, and the actions that come after me should not run. They don't get to go until I'm done. So this is useful, for example, when you're pushing a sequence of commands to move through a path. You want them to move through the first node in the path before they start moving to the second one. Then one of the other companion parts of this is what I like to call lanes, which is really just a bit mask or a set of bits you can set. The idea here is that you can have different actions describing which actions they block or can be blocked by. So the movement actions you can set up to have this bit indicating that they are a movement action, and then they're going to run in sequence. But you then can also have animation actions that won't be blocked and will run sequentially to these the moving actions. And then we also use this for our behavior system. I've got an article online here that goes over how to build one of these in JavaScript. It's a really simple version, but it's got some great implementation techniques there. Moving. All right. So we also used action lists to define all of our AI behavior. There's very few finite state machines in here. They're actually little tiny things. But what we did with the action list is I created what I call behavior composition. And this goes back to the component-driven design, but for AI. So the idea here is that each of those behaviors I listed out originally, instead of being implemented inside of the finite state machine or something like that, were implemented as an independent object that described just that single behavior. And each of these behaviors knew absolutely nothing about any of the other behaviors in the game. For example, the chase player behavior knew how to chase the player. That's it, nothing else. So what we did then is we could push these behaviors into the action list on the stack, and they would each be pushed in a priority order. So the more important behaviors, the ones that should run before the other ones, would be higher up in the stack. So what happens is, a simple example, is we've got the patrol area behavior. So that's getting its update thing called every time, because some of the other behaviors are blocking. So the enemy's moving around in its predetermined path. Once the player is visible to the enemy, the chase player behavior, which is higher up in the stack, sets its blocking flag. So now none of the other behaviors, including the patrol behavior, are getting their update method called anymore. So this means now that chase is running and the other stuff isn't. So it stops patrolling and now is just executing the actions that chase tells it to do. And then when the player is no longer visible, chase stops being blocking, and the patrol behavior starts being run again, and it goes back in its original path. And this allowed a whole lot of flexibility. We could customize our guard behaviors by just dragging and dropping in our editor the order that these actions were in, or these behaviors were in on the stack, and completely change the way the guards would work. We could also remove some of these behaviors from the stack for certain guards. For instance, we have one of the guards is called the tough guard, and he can't be hit with a stunning shockwave. So the stun feature was actually implemented as a behavior sitting at the top of the stack. Whenever one of the guards got hit by a stunning effect, it went blocking, so none of the other behaviors would run, and the guard would just kind of sit there doing nothing. For the tough guard, we simply just didn't push that behavior on the stack, and he was not stunnable. Super simple, super flexible.
Of course, all of that is pretty boring. Let's talk about something fun like math. So we obviously needed some sort of vector and matrix library in order to do all of this in 3D. So what we decided to use was GL Matrix. This was after doing a bunch of testing to see what would be the fastest, as well as what would be the easiest to integrate into our existing engine that we had just started making. GL Matrix was by far the fastest that we could find. Google Closure in a close second, but it was very easy to get integrated, and it was very nice. Of course, math is pretty hard. We had a couple problems using math in JavaScript, mainly the fact that there is no idea such as a constant reference in JavaScript, which means that since every vector is being passed by reference, you're going to be modifying things in weird ways that you don't expect if you aren't very careful about what you're doing. It's pretty easy to fix. You just have to be very careful that you are passing in proper parameters. So let's look at this trivial example. This is just an array function that is creating an array from one point to another. It seems pretty innocent. However, that vec3.sub is actually modifying the start parameter. And so later, if you want to use this function, let's say you make a variable start that is actually a reference to position. This is once again due to the fact that everything is a reference in JavaScript, including vectors. Then later on, when you use ray on that start reference, it goes through that chain until it actually modifies player.position, which is not the intended behavior with this code. It caused a lot of strange bugs where AI or pathfinding would be modifying different positions, and there was no physical reason or anything in physics that seemed to be to blame. Now, in JavaScript, optimizing the low-level math is pretty difficult just due to the fact that where in C++, you could just look at the disassembly and see exactly what that code is doing. And so when you're doing really tight loops, code that's running hundreds of thousands of times a frame, you can see exactly what it's doing and optimize it perfectly. There is a way to look at the assembly code in V8, but that effectively didn't help us just because it was very hard to associate that JavaScript code to the actual assembly being output. What did help us was the Chrome profiler, which helped us identify the slow parts, and then we could simply use intuition and experimentation in order to optimize that code. On that note, make sure that you test all of your optimizations thoroughly. The V8 profiler is actually sometimes unintuitive in the way that optimizes, and so you might write something much cleaner and seemingly more efficient, and the Chrome optimizer might not understand at all, where it did understand your old obfuscated code. This happened to us in several cases where physics would be running much slower after I just cleaned everything up, and so that's definitely something you want to look out for. Finally, probably the biggest issue that we had in terms of optimization was the garbage collector, which we'll be talking about in much more detail later. But essentially, you have to know that vec3.create will create a heap allocated object, which means that anytime you use a vector or a matrix or anything like that, you are going to be adding pressure to the garbage collector, so you have to avoid creating temporaries. We'll go into this in much more detail. Finally, math is hard. This is due to, in JavaScript, being a weak language. It means that things like false, empty string, empty object, empty array, basically anything that it can will convert to 0. This includes null, which means that if you don't pass something into a function, that will be converted to 0, which means unlike in a compiled language like C++, where if you pass the wrong parameter, it will just error. It won't error, it'll just break in weird ways that you're not expecting. There's also the string problem.
Yeah, so there's this, one of my favorite examples of what happened is our editor for a while, this very minor bug, where when it was writing out the JSON files for where enemies should spawn at, one of the components for the vector was getting written out as a string instead of as a number. So the main engine itself was just loading in these JSON files and really wasn't doing any kind of inspection of the data, and was just passing this vector off into the vec3 create function, which also doesn't check its inputs. So we had this nice little 3-component vector sitting there where the y component was the string 1 instead of the number 1. So what then happened when the physics started running is it was just kind of adding the 0 vector for the basic velocity, even though nothing was supposed to be moving. But this, this component was, instead of staying 1, was changing to 10, and then 100, and then 1,000. And it just flew right off the screen. And it took us kind of a while to figure out that this wasn't some kind of weird bug in our math code or a weird bug in physics. It was actually a bug technically in the editor where it was writing out the wrong data. It's just kind of thing where there's no real tools in JavaScript where it's going to automatically find this stuff for you. So it's something you have to look out for, and of course use the usual web wisdom of sanitizing your inputs when you're loading things in, even if it's your own data files that you think you can trust.
So now let's talk about WebGL, which I'm sure a lot of you are interested in. So why use WebGL in the first place? As opposed to many of the other existing ways to do games in browsers, such as Unity or Flash, you don't need a proprietary plugin. Anyone who has Chrome can run our game. It's, of course, also cross-browser. While our game actually doesn't run in Firefox or Opera or any of those right now, we absolutely could take the effort and port it over, but right now we are only using the Chrome Web Store. It is also cross-platform, which means that Linux users can run our game as well as OS X users. And the main selling point being that it does give you full hardware acceleration. It gives you a very similar API to what you would expect natively, which was amazing for us and allowed us to create the amazing 3D world that SONAR is. Now, there's a lot of really awesome features to WebGL. It's extremely easy to use in a low-level kind of way. If you're coming from a DirectX or OpenGL proper background, you'll feel right at home. You have the same kind of API that you're used to. There's also learningwebgl.com, which is an amazing tutorial resource. It's actually probably the best tutorial I found on OpenGL on the internet. And even though it's specific to WebGL, it's still amazing. Then there's another tool that I would definitely like to point out. As they presented earlier, WebGL Inspector is amazing for debugging. Once again, I come from DirectX, which means that I'm used to Pix. And WebGL had basically the same capabilities as Pix, which I didn't expect at all going into the project. And next. However, you won't get the same kind of more modern features in WebGL as you would expect from something like DirectX 10. Things like geometry shaders, instancing, these aren't available in WebGL just yet. There's also the standard problem of just the vague error output with OpenGL. This is a OpenGL standard problem as well. OpenGL will basically tell you something went wrong this frame, and it's up to you to figure out what that was. There's WebGL debug utils, as they also mentioned earlier, that will basically tell you where something went wrong, and then you can actually pinpoint exactly how to fix it.
All right, so I'm going to go over a bit about how to optimize your JavaScript code for a game engine. So one thing to keep in mind is that JavaScript was designed about 15 years ago, really designed for doing simple animations on web pages, doing client-side form validation. It was never meant to be used as a game engine or even for a large-scale application development. And as much as we've seen these amazing advances in the JavaScript optimizers and interpreters and runtimes today, in a lot of cases, these advancements have come kind of in spite of JavaScript's design rather than instead of it. There's a lot of work these optimizers have to do, and there's a lot of things that you can do that will actually screw up those optimizers and make them not be able to do their job. So you got to know kind of what to avoid and what to do in order to make sure that they can do the best job possible. So one of the things that JavaScript currently lacks is any kind of native SIMD math type for vectors, matrices, things like that. While GL Matrix is a really, really great library and is certainly the fastest one around, you're still not going to get the kind of performance out of these that you would expect out of a native development platform. And there's also some caveats having to use this kind of tacked on third-party library, again going with the fact that all these vectors are objects that are going to be created every time you want to make a new vector, and then that leads into the garbage collector issues, which we'll get into in a moment. Another thing to keep in mind that I notice a lot of people don't really seem to grok sometimes is that games are a real-time application. And that tends to be this term that a lot of people kind of get afraid of or get a lot of these weird thoughts about, and some of them are kind of right. The idea is that in a game, you've got about 16 milliseconds to render a frame if you're aiming for 60 frames a second. And if you blow past that 16 milliseconds, then you're going to start getting frame stutter or drop frame rates, both of which can be really distracting and kind of really ruin the game experience. So all those things that you might see people say that you need to avoid in a real-time application, you also need to avoid in a game as much as possible. And one of the things that that does unfortunately include is garbage collection, which is a native part of the JavaScript runtime. So whenever garbage, the idea of the garbage collector is that as you allocate objects, eventually you're going to stop using them. Garbage collector kicks in and cleans them up for you, so you don't have to do all this kind of manual memory management work. But when the garbage collector kicks in, your application stops, because the garbage collector kind of has to do this work without your application running at the same time and confusing things. The way that the garbage collector will kick in is if you allocate enough objects, it eventually decides that you have allocated enough objects that it needs to check to see if there's garbage, and that's where problems start. So the trick to making the garbage collector not run is to basically not create new objects, at least not during the main runtime of your game, when the player's actually in there having fun doing all your action kind of stuff. So there's a few easy things you can do and a few not quite so easy things you can do to help make sure the garbage collector is not going to bite you. The first one is pretty easy, pretty obvious. The new operator in JavaScript creates new objects. If you're calling that inside of your code, like in your physics code or graphics code, you're going to be causing the garbage collector to eventually kick in the middle of your game. So quite simply enough, do not use the new operator inside your main loops of your game at all. And there's a couple of tricks we can do to get around that I'll get to in a moment. One of the other things that maybe is slightly less obvious is the literals for creating objects, the curly brackets on their own, as well as array literals, any kind of string manipulation. These are creating new objects, garbage collector will kick in. But these can actually be a little tricky at times. In JavaScript, there's a really common idiom of using an object to pass optional parameters to another method, especially if you've got kind of a lot of parameters or a lot of optional ones. You see this all over the place as option objects you pass into things like jQuery. And we were certainly using this in a lot of our APIs internally in our engine at first. But of course, these creating objects, garbage collecting, pressure, all that. The trick here really is to just not use that technique. If you've got these functions you're going to be calling inside your main game loop, just make sure they take parameters the good old-fashioned procedural kind of way. And one of the other things is closures. So closure, of course, is a thing where you've got the function that accesses variables from outside the function scope. Using a closure is totally fine, but creating new closures will create an object. So if you've got some kind of code where you actually have the creation of a closure, which is one that has the function keyword before the body, inside one of your loops, you're going to want to avoid that because that will be a problem. That was actually one of our bigger problems in our physics engine, is we were using a few closures here and there. And towards the third month, we realized that that was actually the biggest contributor to our garbage collection problems. Then some of the other things are be mindful of some of the third-party APIs or some of the browser APIs you might be using, any kind of DOM manipulation, things like, again, GL matrices, Vec3, Mat4 types. All of these might be doing object allocations behind the scenes, and if you're not aware that these are happening, you might get surprised by that. So just be mindful of what's going on with any of the code you're using that you yourself have not written. We've got another article online that's got a kind of little bit more in-depth version of some of these tricks and techniques. So again, the fix for a lot of this for the garbage collection is just not use the features that are going to cause the garbage collector to kick in. This can be a little unfortunate in places. There's some really cool features in JavaScript that you kind of need to avoid, at least inside of the parts of your game that are running during the main action. The stuff running that's during level loading or in your menus or things like that where you don't really kind of need this high frame rate stuff, that's fine. By all means, use all the JavaScript features that make your life as easy as possible. But once you start getting in the action, you're going to want to avoid these kind of things. The Chrome debugger also, and the profile are also some great tools to help you find where memory is being created, how much memory pressure is building up, and these will help you quite a bit when you're trying to optimize out the garbage collection stuff. And there's another little trick called private globals, or at least that's what I've called it. I've not seen a better name for it. But the idea here, code sample, is let's say we're talking about the GL matrix stuff and how it modifies the vectors when you're calling these functions. But you don't want to create new temporaries every time you're trying to do a little bit of math, because that's going to start creating pressure for the garbage collector. So the idea here is essentially that you create some global variables that you will use for temporary object space. You can either do this inside of an object, like we had some member variables in our physics system object that we just reuse in all the methods on physics system. Then some of our math library stuff where we knew we needed a couple temporaries, we'd create this anonymous function and then create closures inside of it that bound to these temporary variables. And the idea here is just that you're pre-allocating the vectors you're going to need later on, and you don't have to worry about allocating them later on at runtime. It gets rid of the garbage collection pressure and make sure that you're not overwriting variables left and right.
If you're doing an object-oriented design such as we were, you can simply use that. For example, in the physics code, the physics system had just kind of a list of temporary variables that any function could use as long as it wasn't recursive. So let's talk about the art pipeline. Essentially what we wanted was for the artist to be able to go from Blender to the game as quickly as possible without any overhead. What it ended up consisting of was creating a model in Blender, exporting it using a Python script, rolling it into a tar file using a shell script, downloading it from the server using Ajax, loading it with the chain loader, and finally decoding it into the buffers. What this meant for the artist was they had to export it from Blender and then reload the game. This killed our iteration time in the end.
Yeah. We got an article online here about how the chain loader worked, which is the part responsible for figuring out what to load, when to load, and getting everything loaded before the action actually starts running. So good read.
So I just mentioned Blender. Blender is a free and open source 3D modeling program. It actually has basically the same kind of feature set as something like 3D Studio Max or Maya, and it was perfectly capable of doing everything we needed it to in terms of games. It also had a very extensive Python API. Essentially, if you can do it in Blender, you can do it using Python, which was really amazing in terms of creating our exporter. It's also much leaner than 3D Studio Max or Maya. It starts up when you click it, unlike some programs. However, one of the problems that we ran into is the fact that Blender just went through a major revision change, which meant that many of the tutorials and documentation that are already there were outdated. This is both the user interface as well as the Python interface. Finally, the bigger problem was that very few professional artists are trained with Blender. And so the training costs of getting our artists acclimated with it may have actually been higher than just getting a 3D Studio Max or Maya license. But it's definitely something you should consider. We did use our own custom model format, as I suggest you do, just to get the assets as optimized as possible. We tried two different avenues. First, we tried JSON, which it's very simple. It's just a text-based format, so was able to output that no problem. Then we tried using a binary format. Being the native developers we are, we thought that that would be faster. No. It turns out that using binary in Python, because it's a dynamic language, is kind of tricky. It wasn't too bad. But using binary in JavaScript was extremely hard. You only are really able to do it in JavaScript because of WebGL and the typed array capability. So all that is showing is really, you're going from Blender and Python, this dynamic language, to a hard binary format, and then back to a dynamic language with WebGL. And that just didn't really work out. And as it turned out, after doing some additional testing, the JSON files weren't much larger than the binary files once minified and compressed. And the load time actually wasn't significantly different. So bottom line, don't even invest in binary formats until you're ready to send it to the GPU, and just go with a JSON format. The models are then loaded into the index and vertex buffers, as you would expect. We did support fully animated meshes, including a bit of additional information so that we could debug it and make sure all the animations work perfectly. We actually used baked animation, which means that instead of doing a bunch of interpolation, hierarchical interpolation, actually, for the bones, which would have been a really large CPU expense because of it being in JavaScript, we just baked it all out at export time. And so while there is a frame rate issue, it means that as long as you export at a high enough frame rate, it won't be noticeable. And then we use GPU skinning, which essentially is just a standard implementation for doing animation, and you can find plenty of resources just using Google. So finally, the art and content pipeline wasn't nearly as efficient as we wanted it to be. Essentially, since JavaScript is in this sandboxed web environment, it has very little access to the file system. So loading a file meant you had to open a dialog and select it. Saving the file meant you had to open another dialog every time and save it manually. And there was no way to automate this. There was no way to check the file system to see if a file has been modified. And really, that is the ideal. You want your artist to be able to just save in Max or whatever and have it just automatically change what's in the game, and so they can see it instantly. And that simply wasn't possible with the way that we went about it. Finally, the Blender issue, as I said before, our artists took a significant amount of time to become acclimated with Blender, and so what we really should have done is use an intermediary format like FBX. which will show up in a sec, hopefully.
There we go.
So FBX is essentially a universal format. It's owned by Autodesk. And so what this means is that anything such as Blender or Max or what have you can export to this one format, and then you can go from that format to your custom one. This would have alleviated the binding essentially to Blender, and so we could have had artists work in any program they liked and had no problem. There is only a C++ SDK. I believe it's an XML format as well, so you could potentially read it directly in JavaScript. However, I don't think that would be a very good idea just because there is a lot of bloat to the file. And so really just having a C++ process that then converted directly to your file or your file type would be much simpler. There's also Collado, which is a similar intermediary format.
All right, I'm going to go over a little bit about how you can use some of the other features of HTML5 inside your game engine. So even though we have this fancy 3D game here, it's important to remember that 2D is still pervasive even in a 3D game. You're going to see it all over the place in your HUD, your menus, loading screens, all these different places. And it turns out that in a web browser, you've got this really fantastic 2D rendering engine that's kind of been there for a while between HTML, CSS. Then you've also got these great toolkits like jQuery, Prototype, MooTools, whatever your poser of choice happens to be. And there's absolutely no reason not to use these, at least for your menus and other things that are going to be running in the 2D context of your game. The Canvas 2D rendering context is really easy to use compared to WebGL. Then CSS, especially some of the recent advancements we've seen in CSS. We've got the transitions, animations, even 3D stuff you can do with just pure CSS and get these really nice looking menus and stuff put together with very minimal effort compared to doing it all in WebGL. Screenshot back from the game, you can see here we've got the base game is being all rendered in GL, but all the text you see is just a simple div overlaid on top of the GL canvas. It's just using HTML for running the text. The timer in the bottom right-hand corner is actually a 2D canvas element, so it's this nice little spin-down effect that took very little code to write. The mouse tutorial image, it's all just HTML. So one of the things is that in standard GL or even DirectX, rendering text is actually really tricky. The algorithms for rendering text are not trivial things in the least. And there's really no reason to re-implement that when the web browser can already do it far better than almost any other application on the face of the planet can do. You've got that capability there. You really should just take advantage of that. And the same for menus, any kind of thing that you want to have pop up, move around. A lot of web developers have techniques doing animated pop-up menus and all that. Those work just fine even with WebGL in your application. However, there is one thing to be wary of. Some of the browsers do not yet have great acceleration in the 2D space, especially when you're mixing 2D and GL. This won't normally be a huge problem, but we did find, at least with Chrome 13, which we initially launched on, that if we moved elements around on top of the GL canvas, our frame rate would drop really quickly. The fix for there is just not to move them, and the frame rate stayed nice, fine. This problem will resolve itself within a few browser releases, almost certainly, as we get more and more hardware acceleration in the browsers. But if you're releasing really soon, this is something to just keep in mind. If you run into the overlay problem, there are simple fixes, so don't worry too much about it. Just be aware that you can kind of play with how complex your CSS is and simplify things quite a bit. All right, so I'm going to talk about our editor and our content creation pipeline from the gameplay perspective. So here's a picture of our editor. One of our team members, the other Sean Pierce, put this together. He's got a lot of UI design experience, so he put together this really nice tool for us here. Simple tile-based editor. You can drag and drop the enemies that are in the level, put them there. You have complete property editing, pretty much everything you need out of an editor for a game like this. It's just, again, some of the other features is we did have triggers for doing things like tutorials and a couple other interesting puzzles. We had a script system, then we had, again, tile-based editor. One thing is that we used line drawing for our doors, the breakable glass that we had in the game. This allowed a little bit more flexibility than using tiles. It's kind of a pain to implement, but it actually worked out fairly well, I think. So the editor was written as a separate application. The main content was drawn all as just a 2D canvas, no WebGL, jQuery, and the jQuery UI subsystem was used for all of the 2D elements, or the menu elements inside of the editor. Being a separate app was kind of a problem. That basically meant that in order to test levels, you had to open up a level editor and then save, which is a pain in JavaScript because there's not even a really good way to do that. And then you could load it back into the game. This meant that just tweaking a single tile or single guard had a lot longer iteration time. And this is something you're going to be doing a lot during playtesting in the final crunch period. The primary reason we went with the separate app is because we had such a short development time. We had to start on the editor the same day we started the engine. So you didn't really have a whole lot of collaboration opportunity there, but if at all possible, I highly recommend you go with an in-game editor. It will just make everything so much easier. We did have a custom script engine. This is something that I am a little bit ashamed of. It is a horrible, horrible hack. It really is a monstrosity. But we actually had to do this because we had a couple issues that JavaScript couldn't actually serve as a scripting language inside of JavaScript itself. The biggest problem is that you can't sandbox JavaScript code from itself very easily, or really at all. And we had thought originally about putting our level editor up online so users could create their own levels and share them. But if users could put JavaScript code into the levels, and then that would just run in the context of the game, and that would be horrible, horrible security problems. That just really wasn't something we wanted to even contemplate trying to subject users to. And then also the way that you have to do asynchronous programming in JavaScript is create a lot of callbacks, and it gets a little messy if you've ever seen like a more complicated Node.js callback. You can see kind of all those levels of indentation you end up going with. It's not something our designer really wanted to have to deal with. He just wanted to be able to let's do this, then do this, then do this, then do this. So he had a really simplistic language that we just kind of compiled into JavaScript and ran that way. But you know, if we started seeing sandboxing support in JavaScript or a coroutine facility, we could actually use JavaScript as a scripting language in a JavaScript game. That would be pretty fantastic.
We did have some alternate ideas that we thought of during our post-mortem. We're running a little low on time, so I'll skip to the one that we thought was most ideal, which was essentially to create a native editor that embedded Chromium. This would allow us to, first off, get access to all of the HTML5 and jQuery style features, so we can make the UI very similar to how we did it in the normal level in the editor we did make. But we could also run the game inside that editor, and thus be able to have that high iteration time and just kind of make a quick tweak, play the game, etc. It also would have allowed us to have those file system features that I mentioned before, so the asset pipeline would have been much more optimized.
All right, I'm going to go over just really quickly a few other web APIs that you guys should absolutely be aware of when working on your own games. The first one is the Web Audio API, which launched with Chrome 14. When we initially launched in Chrome 13, that wasn't available, and we actually had to use Sound Manager 2, which is a Flash applet, which was really painful. There's a lot of bugs in the Flash integration on certain browsers, even on Chrome with its Flash integration. There's a lot of latency communicating between JavaScript and Flash. It just really was not an ideal solution. And Web Audio, which we've now updated to use, is just so much better in pretty much every single way. It's something we're going to see other browsers picking up relatively soon. It's a standard, so hopefully that will be available everywhere before too long. Second API you should absolutely be aware of is the File System API. This allows you to save large amounts of content on the user's disk. This was essential for us in our content caching, because one of the things we really wanted to support was offline play. Make sure that users could get on a plane or on a train or somewhere else where there's no Wi-Fi connectivity and still be able to play the game that they've already downloaded and installed. So we would actually, when the game was first run, we'd take all of our assets and store them into the local file system, and they could be accessed anytime later on. This is already supported in most browsers, not IE, but hopefully by 10 that'll be there. And this is really kind of essential if you've got a lot of art assets and you can't trust streaming to always be available to the user. The second API is not yet available. It is the Relative Mouse Movement or Mouse Lock API. This is going to be absolutely essential for FPS kind of games, but it's actually really important for action games too. One of our more frequent bug reports on Sonar was that users will be trying to click around to do to shoot the sound gun around, and they'll actually click just outside the play area, click on a browser toolbar button or click outside the window, and the window loses focus and the game gets interrupted. Really annoying. So this API will allow that problem to be fixed. It'll allow you to basically keep the cursor inside the window so the user can't accidentally close the game or so on. Then the fourth API, also not yet available but will be relatively soon, is the Joystick API, which is also going to allow support for gamepads. And this is actually really important for certain classes of games. I'm a huge platformer fan, and platformers with a keyboard are not fun at all. So be able to plug in an Xbox gamepad or one of the other gamepad devices out there, it'll be really nice for retro games or kind of those things that just don't work with mouse or keyboard. Takes its time.
So in closing, just wanted to basically go over that WebGL is extremely awesome. It was really easy to use, and so I definitely recommend it. Any low-level developers shouldn't be afraid of it at all, really. JavaScript does make it a little bit tricky to do just the kind of hardcore game development that we're accustomed to, and so there are some little tricks that you have to get used to in order to get around that. Finally, the content pipeline is really what will make or break you. You have to be thinking about that from day one. We thought we were, but we did not think about it as much as we really should have and put as many resources into it as we really should have. And finally, there are just a lot of new technologies in the web space that you should investigate, and so those combined with WebGL are going to make it an amazing platform for games in the future. So any questions? We probably have a minute or so left.
What gave you the inspiration to make it a papercraft, visually styled game?
So that was actually came out of a graphics bug, which I was very easily fixed, but it meant all of our characters were flat-faced, and our designers and our artists all really loved that kind of style, and so that inspired us to go in the more papercraft direction.
Okay. I guess the second question that comes after that then, have you actually cut out and folded up any of the papercraft of the models that you produced for the game?
We considered it, especially in terms of marketing materials, but we haven't actually gotten a chance because we've been very busy since launch with other projects.
Thank you.
Since you developed your JSON format, have you looked at Wan Chun's WebGL loader, which was used for Googlebody to load large meshes in quickly?
We actually have not. Well, thank you very much.